All right, this lecture is on electric current. It says electricity is really just organized lightning, and that's a great definition for what electricity actually is. So by the end of this lecture, you should understand the safety guidelines concerning voltage and current. We covered that in the previous unit a little bit. You should also understand how to calculate electric current and what current actually represents. And you should understand the different types of current and the advantages of each. So if we continue our water analogy, we said that water flowing through a pipe has a flow rate, and that's how much water goes through the pipe. Current is just how much charge moves through the wire. So it's very, very similar to the amount of water through the pipe. It's the amount of charge that goes through the wire. 1 amp, okay, we have electron flow. The number of electrons that flow in a wire determines the current, and what we have is we have I equals Q over T. What I stands for electrical current. Okay, it was originally a French term, intensia, which is why it's an I, but it stands for electric current. It's measured in amps or amperes. Q is charge measured in coulombs from the previous unit. T is time measured in seconds. So what an amp really is a coulomb per second. You are expected to know that. There are many different types of currents, or excuse me, there's two major types of currents, which is alternating current, which is one in which you have the voltage that changes from positive to negative, so it produces a current that goes back and forth, like a sine curve. Because the voltage flips back and forth, it's said that the electrons really never go anywhere, but once again, charge doesn't really move. It's really just the energy that moves back and forth. So alternating current is what you get from all electrical outlets in your house. They all provide alternating current, and there are definite advantages for alternating current. Its competitor is direct current. Direct current is where the charge continuously flows in one direction. In other words, there's no movement back and forth between the charge or the voltage, so it flows in one direction. Examples of direct current is what you get from a battery. Really, every electrical device you use requires direct current for the most part. And what it does is it actually has something called an AC-DC adapter, which actually transfers or it changes alternating current into direct current. So that's what your cell phone charger has. There's usually like a black box attached to any sort of charger device. And what it's doing is it's actually changing it from alternating current to direct current. So the whole idea is, well, if everything uses direct current, why don't we just use direct current? And that was kind of this battle between Edison and Tesla. They're probably two of the smartest men who ever lived. And Tesla actually used to work for Edison. And Edison started the company, GE, which is General Electric. It's still around. It's still one of the biggest companies in the world. But Edison and Tesla worked for him and felt that he had been cheated out of several different devices he should have gotten royalties from. So what they decided to do is Tesla kind of split off his own way, and him and Edison got into quite a big battle over what was better, alternating current and direct current. Now, the first city that was actually the first major city to electrify was the city of New York. And so whoever got the contract for New York was pretty much setting what it would be for the rest of the country. Now, Edison was a proponent of direct current, and what he actually proposes direct current because every device uses it. It can operate at a very, very low voltage, and it's what every device is going to use. Tesla, on the other hand, was a proponent of alternating current, and it does operate at much higher voltages, so it's somewhat dangerous. But the key thing is that alternating current can be produced at a power plant that is very, very far away. Edison's direct current actually only acts over short distances, so you're talking about having a power plant in every neighborhood, as opposed to having a power plant that's very far away and can send the electricity over large distances. So to show the dangers of high voltage electric current, Edison actually created the electric chair to show people how dangerous electric current at high voltages could be. And so we all know that we do have alternating current, so Tesla was the one who won out. Now, conventional current is not really something like alternating current or direct current. Conventional current is a relic of when they thought it was the positive charge that moved through the wire. Now, we still draw diagrams that look like this. We know that it really should be electrons because protons don't move, but we actually do know that even electrons don't really move. If you were to measure the speed of an electron, it would travel at about 1 centimeter per second. Now, if you were waiting for an electron to move through a light bulb, at 1 centimeter per second, you would have to turn the light switch on and then wait a very long time in order for that light bulb to come on. So what actually happens is the energy travels through the wire, and it uses charge to do so, but it's not really the electron that's moving. Now, measuring current. We actually can measure current with something called an ammeter, and we talked about this before. It has to be wired in series, and you know what that is now. And what you do is you always start by plugging the cord in here. The alligator clip goes here, and you get a reading. If it is a small reading like such, then what you would do is you would bump it down to the next one, and then you would bump it down to the next one if you would need to. The reason for that is if you put it here to begin with, you can blow a fuse in the device. So it's very important that you start out large and then work your way down. So this right here is actually how you would do this. If you put the alligator clip here, a reading of 1 would be 1. If you were to put an alligator here, it'd be 500 milliamps, or excuse me, it would be right here, it would be 0.1 amps because it'd be 100 milliamps or 0.1 amps. And finally, if you were going to put an alligator clip here, it would make this value 10 milliamps or 0.01 amps. It's very important that you be able to read an ammeter. Alright, current is dangerous. We talked earlier and we said, okay, voltage isn't really dangerous, but do not go and grab a high voltage line. Current is dangerous. Current is lethal. Current, even in very, very small doses, can be very, very damaging to you, especially if it goes across your chest cavity, because your chest cavity, your heart requires an electrical impulse in order for it to function. So we already went over the rules of safety, but always leave the voltage source off. Wear gloves that have very high resistance, remove sweat, and keep one hand in your pocket. And if you don't know the reason why, please refer to the previous video on voltage, and they will tell you exactly why each one of those needs to be followed. So by now you should understand the safety guidelines and how to use them in the lab. You should be able to calculate electric current from charge, and I'm saying you should be able to go from grams to moles to number to charge to current. You should be able to do all of that. And then you should understand the different types of current and the advantages of each. Why do we use alternating current? What is good about direct current that might have been better if we would have used direct current to begin with?